So yeah, so I'm going to be kind of why I'm trying to talk about this work. I have kind of, I guess, inherited Joe's tendency to wander off into a variety of directions and be broad in what I work on. So I have collections of students working on things ranging from cloud economics to multi-agent reinforcement learning, which might seem quite far from each other in some sense, but actually all in some sense. When I think of my story of it, it all traces back in some sense to work I've done with Joe. This is actually one project that has a less clear line to things I started working on with Joe, at least in the way I got started working on it. As you see, it kind of ends up wandering into things that are relate to it. But in some sense, when I sat down to think about what to talk about, I remembered all the many fun conversations I've had with Joe about arguing about definitions or assumptions or axioms, models, and so I think this is this work is kind of the most like that in some sense, in that this has there are no actual theorems per se in this work. It's really a bunch of definitions and examples trying to think about how some kind of concepts from the fairness literature apply more broadly. And this is work with my student Jack Blandon, who's on his way to becoming hopefully not too distant future an academic grandchild for Joe. So what am I going to start out with? So I'll give you some context. People will be very familiar to people who've already looked at these things, but I want to make sure everyone is kind of along on this. Right, if you think about kind of classic classification problems, I give you a bunch of data points x's. They have some say true label y, and there's some kind of joint distribution over these things. And what classic has to do is, right, you want to learn some classifier. It's going to take in the x's and it's going to predict some y. We'll call that the predicted one y hat. And then you're going to minimize some loss function that depends on the true prediction, the true labels, and the predictions you end up making. Right, so this is I think more recently, over the last it's going on about a decade now, of interest in okay, well, what happens if you want to change this to think about the fairness of the way you're treating the things you're classifying. In particular, there's a big literature on thinking about groups of doing it. So I've extended this and have it down, sort of by now a standard way by adding one more variable z. This is kind of some sort of protected attribute, some characteristic that we want to do. You could think about this as a group that a person is part of, and we want to make sure that each of those demographic groups are treated fairly by our classifier. But apart from that, right, you could some algorithms say yes, the classifier should look at the demographic groups to try to achieve fairness. Others say we don't want that to happen. There's various versions of it. I'll just kind of keep the general one, but kind of the problem. Again, there's different ways to do it. You can do it in a constrained way. You can do it other ways, but one natural way to think about this is I want to solve that same problem, but subject to a constraint of being fair in some sense. And but there are by now kind of a wide range of notions for what these fairness constraints ought to look like. One very common one is called demographic parity. And so here the example, I'm going to stick to kind of binary demographic groups for the purposes of this talk, but everything works for kind of arbitrary numbers of groups. And so if I have two groups, this might say that I want to classify members of each group positively. My positive label y equals 1 with equal probability. Right? If I'm a practical application like loans, this says I want to give loans at the same rate to two demographic groups. But I don't want to be kind of biased against either of them in the way I'm determining who to give loans to. So might not be happy with this, right? We don't want to give loans out at random to people, right? Giving out, just being perfectly random, totally random and giving out loans would be kind of fair by that regard. That should be kind of fair by this one too. But you might want to say, well, I don't want to just look at two groups. I only want to give out loans to people who are qualified, or at least among the people who are qualified for loans, for some notion of qualified, say people who will pay back the loans. Then again, I want the same thing. I've added a condition on the true label Y and gotten a different definition, sometimes called equal opportunity. So, and there's a whole profusion of kind of different group fairness definitions. These are probably the two of the most common, but there are many, many more. You can talk about, you could talk about, false negative error rates. There's kind of a whole range of things you can imagine that kind of, defining probabilities using those different variables and saying you want them to be equal, and you can get kind of a wide range of different and this was kind of my, starting point where I came in to kind of looking at this, because actually what Jack and I wanted to do, we wanted to do some actually inverse reinforcement learning things to try to understand, like, could we infer what fair policies people were trying to do in some kind of more complicated setting. And quickly ran into a problem that, like, we didn't know what these definitions kind of meant in settings that didn't look like classic classification. We didn't even know what it meant. It's been a while trying to, like, okay, what does it mean to talk about a fair policy and reinforcement learning? Like, we have all these group fairness definitions. What do they mean in other contexts? And so we spent a while thinking about it and coming up with something. And then we kind of stepped back and realized that actually there was nothing reinforcement learning specific we had done, and that's kind of the the story. And in some sense, we're not the only people to have gone on this journey. In fact, lots of people who have gone on versions of this journey, and that's kind of the purpose of kind of the theme of this talk, is that in some sense there are lots of places where these basic definitions, you can't literally apply them, and so the goal is to provide kind of a general framework to understand how you can apply them in a wide range of contexts. And to do that, I'll kind of talk about, like, what are some of the kind of assumptions that are baked into these definitions, if you just take the basic definitions, that are not generally true in other contexts. And again, I'm not going to claim that, like, any one of these like these assumptions, like the observation about these assumptions, are novel. In fact, like, all of them, I can point you to related work that previous to us had focused specifically on each of these issues. I just want to give you a sense that these definitions break down in a lot of ways. Right? And so, one thing, for example, is that, demographic parity says that, okay, we want to give loans to these two groups at the same rate, right? We want to give them the same rate of y hat equals 1, right? But is that actually what we want, right? Like, if I give somebody a loan and then they default on it, was that actually a good thing for them? Right? So it's not clear that, like, just being given the positive label is the thing that people want. You might, want.
What they want. It's not really good for them.
Exactly. So it's a question of, yes, whether people
you get what you need.
yeah. Right. And so kind of another assumption baked into some of these definitions, from that definition of equal opportunity I had, involved, like, conditioning on kind of the people's true label Y, right? And you might think of like the true outcome that would happen if you gave them a loan, for example. The kind of the fairness formulations assume some sense that the outcomes are independent of that. And so kind of see where this can kind of break down and lead to kind of sort of self-fulfilling prophecies like behavior, right? So take as take as your uh, you know y hat. Uh, this person got admitted to some PhD program, and take as your why this person became a professor, right? And so you know given that at least in computer science it's virtually required to finish a PhD before you get tenure track professor position, right? Well, you could say, sure, according to this definition, right? Everybody who was qualified, everyone who did in fact become a professor, right? They were admitted to the PhD program. So whatever way we admit people to PhD programs, perfectly fair, right? It's we get exact equality coming out of this, right? Because there's a self-fulfilling prophecy coming. Yeah.
The problem is assuming that y is a function of x.
Right, exactly, right. And this is my point, right? So if you just take these definitions as
but y is, as we know, qualified for PhD doesn't mean you finish the PhD, right? Y is really a probabilistic outcome.
Yeah, right. So certainly, yeah,
probabilistic.
Yep. Yeah, and this actually, I'll get back to that point later. That's kind of one of the kind of the degrees of freedom where you have some decisions about what to do that I'll talk about later. Exactly because these things are probabilistic. Right. Assumption 3, and this is kind of where we first hit a pain point, right? Like that our goal is somehow to choose a y hat that, like in classification, is supposed to somehow match y, right? That we're sort of kind of predict the true label or something like that. And there's lots of applications you can imagine having, like demographic sorts of various data about individuals, and then you're going to take some decision, but like if your reinforcement learning is like which action to take at this stage in the process of the person, or you're clustering, like what cluster am I supposed to assign this person to? Like, not clear at all what like the y is that you're supposed to have a y hat matching. Like, it just doesn't really make sense in other contexts. And it even for those definitions kind of assume that what y hat I assign to one person doesn't affect somebody else, right? So if they're if I'm doing some clustering thing for like assignment to congressional districts, I really might care who else is in my district, right? Or people are embedded in some sort of network, then what I do to one person may have effects on the people who are around them, right? So as I said, none of these are original observations. Like the loan example is a very classic violation of assumption 1, and there's lots of papers looking at specifically. This is just kind of like a short list. Specifically, there's many kind of special cases of assumption 3. I'll come back to that later, and we'll look at a few of them. But I kind of want to step back and looking at kind of grouping a lot of these kind of complaints as right. And at least 3 of the 4 assumptions are really about what people want, right? Or maybe what they ought to want, right? We're going to have that debate. But a lot of those assumptions are really about, right, what people want. Well, these are really all about people's utilities, in some sense, right? When they want to talk about, like how happy people are at the outcome, or what is it we should be choosing for people, or how are people affected? Like, those are things we can capture with a utility function. How, right? And indeed, again, like we are certainly far from the first people to say, oh, let's think about using utility functions in these fairness contexts. There's what work that's thought about credit scores as utility functions, or we'll likely see an example of this later, that kind of actually optimizing for utility sometimes is a good thing for for fairness, or actually some work that kind of came out while we were kind of along this journey that looked at this idea specifically in RL, but generally this has been like looking at utility in a specific application to solve a specific problem. Or actually, kind of the argument that I want to make is kind of utility is a generic framework to think about solving all of these problems, right? And in some sense, we kind of already had one utility function floating around from the very beginning, right? Which is the decision maker had some loss function that captured how they felt about different sorts of errors in their classification problem. And so really to kind of capture this, we just need to add one more kind of utility, which is the utility of the individual that the decision is being made on. So W for that. I'll use L for the decision maker loss, kind of keeping with a loss rather than the utility, just because that's kind of the more common phrasing from a machine learning perspective, right? And and as we were saying that there's definitely like some randomness going on in like what somebody's utility ends up being, right? Even if I determine it, even if I so this is kind of I'm sampling from a population, right? There's going to be, as with all of these, some which individual I ended up choosing, and then my algorithm might be randomized, right? And we have to kind of think about how to define and talk about these things. And kind of what we argue actually is the way you should define W is for looking from the perspective of an individual, you should look at their expected utility. It's kind of a very kind of standard way to think about what happens from an individual's perspective. And so we kind of define W in that way. And then the question is what to do about the randomness of the individual, right? So now, if you think about it, right, what we have fundamentally is I have two groups, and I can give you the distribution of their expected utilities under my classifier algorithm, whatever it is. And so now, what should I compare? What should I insist be the same between those two distributions, right? You can insist that those two distributions be literally the same. That's a very strong assumption and like severely restricts the sorts of things you're actually able to do if you wanted to do that, right? You could, compute some statistic or property of the distribution and say, I want those to be the same. Like, if I want them to have in expectation over what individual is chosen, I want them to have the same expected utility. That felt at least to us a bit odd in terms of fairness, right? That kind of runs really strongly at kind of the critiques of utilitarianism. If we're just saying, treat this whole group of people in terms of its expected utility, and then we'll say we're treating them fairly. So what we kind of settled on that felt naturally argue for is a way you should think about this is pick some expected utility threshold that represents a good outcome for an individual, or the individual kind of does well by this. And the thing we'll want to ask is, did they end up, in expectation? Does this algorithm do well for them? And again, like there's some freedom to choose how you do this. I'm not 100% confident that we settled on kind of the right decision point in this space, but that's kind of one of the places there's some flexibility in this modeling is how do we choose when what it is that we want to compare. But having defined kind of this one more variable in this threshold, now you can take this definition of demographic parity that was defined for a classification setting and really apply it in just about any setting that you want, as long as you can define what that measure of welfare for the individuals being decided on is, and what thresholds you're going to want to use to make them happy. This really is, it's not too hard. We work out in the paper. You can really show that this really does generalize the classification definition by kind of just embedding things. Okay, so that's one part of the story. A big chunk. You thinking about utilities lets you take all of these group fairness notions and think about them in a much larger range of settings. But I may have remembered when I had that slide, I said assumption 1, assumption 3, and assumption 4. What about assumption 2? And that was all about this issue of, sometimes Y shows up there. What even does Y mean in these settings for things like equal opportunity? This is kind of the second argument we make. This is, you might have noticed there's the word counterfactual in the title, and we haven't talked about that yet. And that's where this comes in. So we thought, okay, what do things like equal opportunity mean? And the sort of the standard philosophy is we want to ensure that qualified individuals are treated fairly. Well, like similar, what are some kind of examples of kind of the sorts of things people mean when they have qualified people, right? Well, maybe if I have skilled job candidates, right? I want their hiring to be, independent of what group they're from. Or if I have, some, straight A student, again, maybe I want their probability of admission to be independent of some particular demographic group. Right? And kind of interrogating, these things a bit more, like what is going on in those sorts of examples, right? What is kind of the general notion of qualified? And we kind of argue that it's a notion of mutual beneficence. So like there are people for whom you can make a decision that's positive both for them and for the decision maker, right? So like, what makes a skilled job candidate skilled? Well, they will do a good job for the employer. What makes a like why do universities want to admit students with strong high school grades? Well, that's very predictive that they'll go and do well at university and reflect well on the university that admitted them. Right? And so, in order to then talk about these, right, we need able to have some notion of counterfactual floating in to be able to talk about what would happen under some different policy, right? Because all of those were kind of counterfactual statements about what would happen. Maybe if I gave them the job, and you can sort of define a random variable that kind of captures this idea that there is some algorithm that leads to a good result with that individual for both the individual and the decision maker. And then again, you can use this notion to generalize equal opportunity type notions that rely on the notion of qualified people to a variety of settings. So kind of that's the core idea, that you can use utilities and then this notion of counterfactuals to get mutual beneficence to apply these group fairness definitions in kind of a range of settings. And then kind of going back through each of these, kind of illustrating how these things work. Why how does utility good? This is sort of I won't even explain the experimental setup in detail. It's not important. It's all in the paper if you're curious. But basically, one thing that's received a lot of attention is trade-offs between efficiency and fairness. Right? So here I have on the y-axis I have outcomes that are better for the decision maker. On the x-axis I have outcomes that are fairer. And this is even just a simple classification example. Right? So I'm sticking within the classification framework for this, and it sure looks like among these kind of clusters of algorithms, there's kind of a trade-off between efficiency and fairness. There's kind of one of these algorithms. You'll be up here in the efficient but less fair, or you can move down here and be less efficient and fairer.
Where do you get the counterfactuals from?
So this is actually there's no counterfactual. There's no. So this is demographic parity. So the counterfactual side of things doesn't show up here. So you're talking about for this one.
Like in the definition, you have it there, but where does the counterfactual model come from?
Yeah. So that's kind of a question that we punt on in some sense, right? Like we say, like clearly there's like a causal inference piece if you want to be able to apply these definitions in practice, and so we kind of punt on that and point to the, there's actually quite a large literature on causal things and fairness that kind of gets at some of these questions. Yeah, exactly. And so so we kind of rely on that as a piece, and again we're much more focused on like the definitions and how to think about it than the algorithms. Yeah. It's like the one experiment in the paper, and even it is more a proof of concept demonstration or an illustration than a real experiment. And just kind of the takeaway actually with this is, assumption one was about like the importance of thinking about like just positive labels are not the right thing, because it turns out then if you start applying some weights to people who that factor in that them ultimately defaulting on a loan is a bad thing for them, you make that assumption, then suddenly actually the whole efficiency fairness trade-off you thought you had disappears. Actually, the algorithms that seemed more efficient actually end up being fairer when you start thinking about the outcomes for people rather than just the standard thing of did they get the positive label. And again, as I said, like this, this not necessarily an original observation, but I want to show how it falls very naturally out of the utility framework. So there have been lots of looking at these concerns about causality here, and so this is thinking so sort of recidivism and sort of one example of this, and thinking about whether kind of detaining or releasing someone ahead of trial will lead to future issues or not. And so this is from an approach that kind of broke them up into kind of what they call principal strata that kind of broke people up into groups depending on how they would respond to various treatments, is the essential idea behind their approach. And so you have some people that kind of what your whatever you did didn't have any causal influence on them. So like say people are not going to commit a crime in the future no matter whether you detain them or not. Generally dangerous people, whether you detain them or not now, they're going to go off and do something bad in the future, right? And so for this notion of like who's qualified for the purpose of these self-fulfilling prophecies, like there's no kind of disagreement between kind of our approach and others on this. But when you start talking about people who will if you detain them, then will go on to do something bad in the future, but wouldn't if you hadn't detained them, or similarly people who would go on to do something bad if you didn't detain them, but by detaining them you somehow prevent that, right? When you have those groups where there is kind of a causal effect of what you do, right? Now kind of the things that come out of our framework and the classic definitions disagree with each other. And I won't kind of go through the whole example, but you could probably imagine that you can use this to construct cases where the traditional definitions would say, yes, you're being perfectly fair, but actually you can show that this is happening because of self-fulfilling prophecies. You're playing weird games by choosing which in those categories where you have a causal influence over, you can do it. And and so there is the definition that falls naturally out of our framework is actually kind of a slightly less restrictive version of what they come up with in this paper. Essentially, they impose even stronger conditions about kind of treating all four of these groups equally, where we are just concerned about the just kind of people who are qualified in our sense and unqualified based on what outcomes we can achieve for them. But we actually show that like you could use the same approach that we use actually to get their definition by adding kind of another random variable in the spirit of that gamma into our framework. And then, as I mentioned, there was like too many examples to cite of this case where people ran into problems with kind of the standard definitions and had to figure out something else, and that we were not the first to go on this journey. And if you look at the papers in this literature, you will find many quotes like these, where they say something like, this is what we're imposing is similar to an analogous constraint from the classification literature, or you can take what they did in that literature and extend this star constraint. And these are examples from ranking and reinforcement learning. People have come up with things, or examples from clustering, which then this then translates, or this is the equivalent notion of. But there's been kind of this kind of bootstrapping step in many papers where people have kind of had to make an argument that, oh yes, this is somehow the right translation or extension of these things into the setting we care about. And kind of one of the things we argue is, if you buy our general framework, then you don't need to come up with kind of these bespoke translations. What all you need to do is come up with, define your utility function and your threshold, and then the definitions that people have used in many of these papers just fall directly out of our framework once you define what the welfare of individuals means in that setting. And indeed, you can get kind of very different fairness things people have come out. And like what this kind of pins down in some senses, like you can find in that clustering example, those were two different papers that gave very different translations of the same demographic parity definition. The difference was they were basically using different utility functions for people. And so that kind of falls directly out of what we said. So kind of, my main takeaway is, we can, there are these, if you just look at it from the classification, these definitions are tightly linked to that setting, but you can use utilities and counterfactuals to generalize them and recover many of the bespoke variants people have come up with literature. Normally, I would, conclude here by, thanking you, the audience, but I think, it's really, thanks, Joe, for your help and influence along the way.